Okay, students, we're going to continue our discussion of the properties of gases. In the previous section, we arrived at the ideal gas law or ideal gas equation, PV equals nRT. Now, we arrived at this law by combining Boyle's, Charles's, and Avogadro's laws. But let's do this in reverse. Let's say that we start with the ideal gas law. And let's look here on the left side as we consider what if the number of moles N and T are constant. If we rearrange the equation for the volume, we see that the equation has V equals nRT over P, where everything on the top part of that is a constant now. That means that it's telling me that the volume is inversely related to the pressure. That's Boyle's law. In the middle branch here, you can see that constant N and P, we have V equals nRT over P, and the variables that are highlighted in kind of like a red color here are all constants, which means that volume is directly related to temperature. That's Charles's law. On the right branch, we see that at constant pressure and temperature, nRT over P, since RT and P are constants, volume is directly related to N. In other words, we have Avogadro's law. So you can go in both directions. So let's do this. Let's use this process to derive a quote-unquote new relationship or new law. Let's look at an example. Argon is an inert gas used in light bulbs to retard the vaporization of the filament. Let me make a pause here. You know what I'm thinking, that in a few years, if I give this example, the next generation of students are going to ask, what is a light bulb? What is a filament? Because as you know, most of the incandescent type of light bulbs are being replaced now by, fluorescent and LEDs. And so this is kind of like a little old school here. But yes, in case you're not familiar with this, the way a light bulb used to work is you have a filament and there is an electrical current that runs through it. When you turn it on, it causes it to heat up and emit light, which gets amplified by the glass in the light bulb. And this has to be sealed in order for the filament not to, get eroded and broken down. Okay, back to our problem. A certain light bulb containing argon at 1.20 atmospheres and 18 degrees Celsius is heated to 85 degrees Celsius at constant volume. Yes, light bulbs get really hot. What is the final pressure of argon in the light bulb? Now notice that we're talking about a relationship between pressure and temperature. We didn't see any of those laws, right? Neither Boyle's, nor Charles's, nor Avogadro's having a relationship between pressure and temperature. So let's derive it. PV equals nRT. So let's say that, for example, in this case, the number of moles of gas, because the light bulb is sealed, is the same, all right? The volume is the same. We're assuming that the light bulb does not expand significantly. And of course, R is a constant. So all three of these are constants, N, V, and R. So that means that if we rearrange this equation as a relationship of P over T, let's divide by T on both sides and by V on both sides, and we get NR over V equals P over T. And because N, R, and V are constants, this is a constant. So just like we did before between volume and temperature, we can say that P1 over T1 equals P2 over T2. Notice how we derived this relationship. Actually, this is another law that was derived experimentally by Joseph Louis Gay-Lussac, and this is called Gay-Lussac's law. But we derived it from the ideal gas equation. So we have the pressure and temperature that we start with, and we have the final temperature. So we need to find out what is going to be the final temperature, P2, right? So P1 is 1.20 atmospheres. T1, we're going to convert it to Kelvin, and it's 291. T2, 85 degrees Celsius, is 358 Kelvin, and our unknown is P2. So let's take this law that we derived, or actually we copied from Gay-Lussac, and let's rearrange it to solve for P2. Let's put the numbers in, atmospheres, temperatures. Careful again when you are moving around terms in fractions, make sure you put them in the right place. Now, we know that pressure and temperature, according to this, have a direct relationship. So if I am increasing the temperature, I should also experience an increase in pressure. So that's how we're going to check if our numbers make sense. Okay, Kelvin cancels out, and we arrive at the final result, 1.48 atmospheres. As predicted, the temperature increased. Okay, let's do another application of the ideal gas equation. And that has to do with measurements of mass. Remember that we've said that in the lab, the property that we can measure with perhaps the best accuracy is the mass of a sample. So let's talk about densities. Let's say that I have a known gas. In other words, I know what its identity is, and therefore if I have a given mass of it, I know how many moles I have because I know the molar mass of this gas. So PV equals nRT. Let's say that I know who the gas is. I can find the number of moles by dividing the mass in grams by the molar mass in grams per mole. Notice that grams divided by grams per mole gives me moles. So all I'm doing here is I'm converting N into units of what I can measure in the lab, which is mass, and what I know is the molar mass of this known gas. So I'm going to go ahead and say that if I take now this equation and I rearrange it as a mass over volume relationship, I get the molar mass times P divided by RT. And remember, grams per liter would be the density. So I can predict what will be the density of a known gas under specific conditions of pressure and temperature. And if I know the number of grams, actually, I can calculate how many liters that sample is going to occupy under those conditions of pressure and temperature. So I think as you think through it, you can imagine what are some of the typical types of questions that we could ask and answer using this version of the ideal gas equation. Now, what if I don't know the identity of my gas? Well, here's where the ideal gas equation becomes very interesting because we can use it to calculate the molar mass of an unknown gas. Remember we said back in chapter 3, in unit 3, that one of the main tasks that we have is to find out what is the molar mass, the molecular weight of a substance, so that combining that information with the composition, we can find what is the chemical formula of the compound. Well, here we go. For gases, we can use the ideal gas equation. Let's go back to this equation we had above and let's rearrange it again to solve for the actual molar mass of the unknown. That'll be dRT over P, where D is the density in grams per liter. Notice that if you walk through the units of this, density in grams per liter, units of R, temperature in Kelvin, pressure in atmosphere, everything will cancel out except for the grams per mole, and that is precisely the units we're looking for. Let's do a little practice exercise with this. A 2.10 liter vessel contains 4.65 grams of a gas at 1 atmosphere and 27.0 degrees Celsius. What is the molar mass of the gas? Notice that what I've done with this, let's say for example, I have this gas, I'm going to analyze its composition, and now what I'm going to do is I'm going to put a certain measured mass in the vessel. Probably the way I did it was I took the container, I weighted it empty, and then I put it a certain amount of gas and determined that the difference was 4.65 grams. So I know what is the mass of the substance that I put in there, right? So I have now the mass, I have the pressure, the temperature, and the volume. Let's calculate the molar mass. Here's the equation that we derived last time. Let's see what the density is. It would be the mass divided by the volume. So we have 4.65 grams in 2.10 liters. So that gives me about 2.21 grams per liter. And now what I'm going to do is I'm going to plug these numbers over here in this equation that I derived on the left. Okay, so the molar mass is going to be all of this. Let me give you a chance to look at that. That's the density times R times the temperature. Notice that because the Celsius was given as 27.0, it has 1 decimal. So the Kelvin conversion is going to carry 1 decimal still. The pressure is given to 3 sig figs. So our final result based on the density and the pressure will be 3 sig figs. Let's see what we get here. Make sure the units cancel out. So liters cancel out there. Kelvin cancels out there. And atmospheres cancels out here. Remember that it's not degrees Kelvin, it's just Kelvin. So the units left standing are grams per mole, which are the correct units for molar mass. That means that we at least have it set up the correct way. Let's put the numbers into the calculator, and the result we get is 54.4 grams per mole. Notice that now I would be able to take this information together with composition analysis and arrive at a formula for my unknown compound. Excellent, right? I'm glad you agree. All right, let's look at another application of the ideal gas equation. In the previous unit, we talked about stoichiometry. We said that one of the important applications of a balanced chemical equation is that it allows me to connect the amount of, let's say, one reactant to another, or the amount of a reactant to product. We can calculate the yield, both the theoretical yield and the percent yield, etc. In those cases, we worked, first of all, with pure substances, typically amounts given in grams, and we had to convert them to moles. So we could transact things in the equation because the units of the chemical equation are moles, right? Then we added another dimension to it by saying, well, we can also do the same calculations with solutions if we know molarities and we have a volume of solution which we can convert into moles. Now we have a third dimension to this. We can do this type of calculations with gases. So let's look at an example here. What is the volume of carbon dioxide produced at 37 degrees Celsius in 1 atmosphere when 5.60 grams of glucose are used up in the reaction that is written here? And hopefully, as soon as you see that equation, you can recognize this is the type of reaction that we call, that's right, a combustion reaction. Very good. Okay, so let's do our little map here. We're going to start with grams of a reactant, and that's glucose, C6H12O6. We have to exchange currencies into moles, so we can use the stoichiometric coefficients in the equation to find the moles of product, CO2. But in this case, the question is not how many grams of CO2 we get, but what volume is it going to occupy? So we're going to have to use the ideal gas equation in that last step. For the sake of illustration, I'm going to split it into two sections here. Let's first find out how many moles of CO2 we can produce. So start out with the grams of glucose, and you should be able to calculate the molar mass given the formula. I'm going to simplify it to 3 sig figs here. 180 grams of glucose is 1 mole. And then I'm going to look at the chemical equation that says that I can get 6 moles of CO2 for every mole of glucose. And just like we did in the previous unit, we're going to make sure that the units cancel out, grams with grams, moles with moles, all of that glucose. And the final result should give me the moles of CO2 product. Again, notice I could have chosen to use the full molar mass of glucose to 2 decimal places, but I was going to have to round it anyway. I can leave it in my calculator. Remember, in the end, we do the rounding in the last step. So let's say we get 0.187 moles of CO2. That is our theoretical yield. Now, what volume will that amount of CO2 occupy? Well, we're going to use the ideal gas equation. The volume would be nRT over P. We have the number of moles. We have the temperature, although we had to convert it to Kelvin. We have the pressure in atmospheres. we had the value of R. Let's plug all these numbers in there. Okay, let me give you a chance to copy those down. If you want to pause the video, you can do that while you write them down. And now put the numbers in your calculator to see what we get. Let's check the moles, and moles cancel out first. Check out the atmospheres, they cancel out. Check out the kelvins, they cancel out. You have, in the end, units of liters. That is what we wanted, right? You always make sure you do these checkpoints, right? Before you plug numbers in the calculator and get anything out there, make sure that you're gonna get the correct units. And the result is 4.76 liters. Again, 3 sig figs is what we get here. Okay, so far we've seen, 3 applications of the ideal gas equation. Number one, we can use the ideal gas equation and retro-derive gas laws, such as the one we derived for the pressure versus temperature relationship, right? Secondly, we can use the ideal gas equation to find the molar mass of an unknown if we have a given mass and we measure what volume it occupies at a certain pressure and temperature. And thirdly, again, given conditions of temperature and pressure, we can use calculations of stoichiometry and find gas products or reactants in terms of, let's say, volumes at a given pressure and temperature. Now, one question I would have is, how would you have harvested this CO2, right? How would you recover it and find out, well, what volume did I actually get so that I can find what was actually my percent yield? Well, one of the ways that we do this is by harvesting gas products over water. Here's an example of an experiment where we took potassium chlorate, and there's also something in there called manganese dioxide, and we're going to do that experiment actually in one of our lab activities, and MnO2 is going to serve a purpose as something called a catalyst. We know that KClO3 decomposes, and one of its products is oxygen gas. So as you can see in this apparatus, we're collecting that oxygen, we're letting it bubble into a bottle that originally was full of water. And so we started out here with a bottle filled with water. We placed it upside down in this basin, and we allowed the oxygen gas to bubble in and be collected as oxygen gas. Here is the actual chemical equation for the reaction that we're studying. And again, here is the oxygen gas that we're collecting. Now, how would I know what's in here? Because here's the problem. Besides the oxygen gas I collected, the water that was in there, as soon as there was room above it, as soon as the water started getting displaced, some of the water vaporized. And so that bottle has both oxygen gas, and water vapor. How do we tell them apart? Well, there is another law, and it's based on the idea that in a mixture of gases, the partial pressure of a gas is the pressure that the same amount of gas would exert by itself at the same temperature and in the same volume. The idea here is that each gas in the mixture behaves independently of each other. And this gives rise to what we call Dalton's law of partial pressures. Let's say that I start with a container here on the left, and it has a gas marked here in red, all right? And we're going to say that it has a pressure of P1. And now I have another gas here that has a pressure P2. You can see the gauges on the top. They would be indicating the relative pressures. And let's say that I combine these two gases at the same volume and the same temperature. What I'm saying is that at the end, the total pressure is going to be the sum of the partial pressures of each one of those gases respectively. This is Dalton's law. The total pressure in a mixture of gases is equal to the sum of the partial pressures of each gas. In other words, the pressure that each one of those samples of gas would occupy in the same container, same volume, same temperature. Let's do a little derivation here so we can see how this works. Let's consider a mixture now of two gases, A and B, and I've gone ahead and put A in red and B in green in a container of volume V. Dalton's law says that the total pressure should be PA plus PB. So according to the ideal gas equation, what would be the partial pressure of A? It would be nRT over V, but in this case, we're going to put N sub A as the number of moles of that specific gas A. Similarly, for gas B, the number of moles of that particular gas is going to generate a partial pressure we're calling P sub B. Let's do a trick here. Let's see what would be the ratio of, let's say, the pressure of gas A to the total pressure in the chamber. Well, remember, the pressure of A we have here is NA times RT over V. The total pressure in the chamber will be the sum of the pressures of A plus B, which, all things being constant, RT and V being constant, means that what you have here is NA plus NB times RT divided by V. Now, because R is a constant, the temperature is constant, and the volume is constant, all of those units cancel out and we're left with this ratio. Notice how interesting this is. The ratio of the pressure of gas A to the total pressure is equal to the ratio of the moles of A to the total moles in the mixture. So let's define that ratio as the mole fraction of A. This is another way of, by the way, measuring concentration in a mixture. We may have alluded to it earlier, but it is another way. It's a ratio of the moles of one particular component to all the components in the mixture. Notice that we could do the same thing for gas B. We could say that for gas B, the mole fraction of B is the ratio of the moles of gas B to the total moles in the mixture. So let's look at A here. If we clear it out, if we rearrange that expression, we can find that the partial pressure of gas A equals the mole fraction of A, which we found over here. Remember, we found this value here. That's the mole fraction of A times the total pressure. Same thing for B. The total partial pressure of B would be the mole fraction of B times the total pressure. In other words, for any gas in a mixture of gases, according to Dalton's law, its partial pressure is going to be its mole fraction times the total fraction of the mixture. Let me give you a few moments if you want to pause the video now to review this, make sure you understand. This is not very complicated math, but you might want to review it back because I may have gone a little fast through it. Okay, let's go look at an application of this. A sample of natural gas contains 8.24 moles of CH4, 0.421 moles of C2H6, and 0.116 moles of C3H8. Actually, these compounds are called respectively methane, ethane, and propane. If the total pressure of the gas is 1.37 atmospheres, what is the partial pressure of propane? All right, well, let's go and look at this. And let's say that the partial pressure of any gas will be its mole fraction times the total pressure. In this case, we're saying that the total pressure in this sample is 1.37 atmospheres. They don't tell us the temperature because for this type of calculation at this point, it's not relevant. So let's see what is the mole fraction of propane. Propane is the, C3H8 component. So we have 0.116 moles of that compound divided by the sum of all the other ones. And you can do that in your calculator and you find out that ultimately you get 0.0132. That is the mole fraction of propane. Now let's find out what is its partial pressure. It will be the mole fraction times the total pressure. So 0.0132 times 1.37 atmospheres. And you can see because the mole fraction is a ratio, the units cancel out. There's no units in it. It's just a fraction. We get 0.0181 atmospheres. Okay, so that's an application of this. Now let's go back to our original question, which was, how do I deal with gas collected over water where I have a bottle that is full of oxygen and water vapor? Well, again, here's our equation. We're interested specifically in how much oxygen was produced. So how do we eliminate the water vapor? Well, remember, the total pressure inside this bottle is going to be the sum of the partial pressure of the oxygen plus the partial pressure of the water vapor. I can measure the total pressure. We're going to learn a technique for that. It's actually going to play a little trick to find it in our experimental activity coming up. But what about the vapor pressure of the water? Well, it's been done for us. It turns out that the pressure of water vapor above a sample of liquid water is directly related to the temperature. It's not a linear relationship, but scientists have built charts like the one we have here on the right, where you have the pressure of water vapor at different temperatures. So in essence, what I have to do is, coming back to our experiment here, if I know what is the total pressure and what is the temperature at which I collected this sample, I can go to this chart and find out, okay, at that temperature, let's say it was 25 degrees, water vapor, it says here, would exert a pressure of 23.76 millimeters of mercury. So all I had to do is subtract that from the total pressure, coming back here, and I can find what is the partial pressure of oxygen. Okay, let's close out with a practice exercise. It may be that this slide didn't make it into your particular handout set, so I'm going to give you a chance to look at it. We're going to solve this on paper. So it says magnesium was reacted with excess HCl according to the following reaction, and you recognize that hopefully as a hydrogen displacement reaction. It's a redox reaction, and it says that the initial mass of magnesium metal was 0.0426 grams. The volume of the gas produced was 41.75 milliliters. The pressure of the gas is 740.8 torr, and the water temperature is 24.1 degrees Celsius. In other words, it's obvious that in this case we collected the magnesium product here, the hydrogen gas, right, the product of the reaction of magnesium and HCl. We collected it over water at a temperature of 24.1 degrees Celsius. The question is, what was the percent yield? Let's go to our paper board here and solve this problem by hand. Okay, students, let's go ahead and see how we would solve this. A couple of things first of all. Information given. You have the equation, you have the initial mass of magnesium metal, and then you have the volume of the gas produced, the pressure. Notice that it says of the gas. In other words, this amount has already been corrected for the vapor pressure of water. So this is the actual partial pressure of the gas product, the hydrogen. And then the water temperature is 24.1 degrees Celsius. And then it asks you for the percent yield. So what you need to do is you need to strategize here. Think about what exactly is it that I'm doing here. If I want to find out the percent yield, that means I had to find out what is the actual yield. And I also had to find out what would have been the theoretical yield. So we can start with either one of those. Let's start out with the theoretical yield. Okay, so let's do strategy here. Let's do number one, find the theoretical yield. And this is all done by virtue of stoichiometry, right? So we have a total of 0.0426 grams of magnesium. Remember, in order to transact in the chemical equation, we had to convert that to moles. So let's see what is 1 mole of magnesium. We're going to go to our periodic table, right, as always, and we have it here at 24.31 grams. 24.31 grams of magnesium. That's going to take us into the territory of moles. And according to the chemical equation, we're going to get 1 mole of H2 for every mole of magnesium. So that'll cancel out the moles of magnesium. And let's see what that leaves us with. So we have 0.0426 grams of magnesium divided by 24.31 grams times 1 over 1. So I have 1.7523. Our value here only had 3 sig figs. Remember that we measure typically masses in the lab to 4 decimals, but unfortunately this one only has 3 sig figs. So we're going to say this is 1.75 times 10 to the negative 3 moles. That is our theoretical yield. Now we need to find what is our actual yield. Find the actual yield. Well, what we have here is we have a volume, we have a pressure, and we have a temperature. The problem is that those are given in units that if we want to apply the ideal gas equation, they're not going to work out. We have to change them, right? So let's go ahead and change all of these. First of all, let's start with what is the pressure of the hydrogen gas. It says here 740.8 torr. Remember, torr is the same as millimeters of mercury. And we know that 1 atmosphere is 760. But since this is an exact relationship, I'm going to add a little, oh, sorry about this scratchy there. 760.0 torr. Sorry, this is a T here. I just kind of like, this marker is a little too thick. Okay, so we're going to convert that, and that should give us 0.9747 atmospheres. That's the unit that we want in order to plug into the ideal gas equation. Let's look now at the volume. It's 41.75 mLs, right? But we want to convert that to liters. Remember, 1 liter is 1,000 mLs. So that means this is going to be 0.04175 liters. And those are the units we want for our ideal gas equation. And last but not least, we have the temperature. We said it was 24.1 Celsius. We're going to add 273.15. But because the input number only has 1 decimal, we had to round our result to 1 decimal. So this is 297.3 Kelvin. Remember, in order to use the ideal gas equation, or actually any calculations that involve temperature with gases, we have to use Kelvin. So what we're interested here is how many moles did we get. So let's go ahead and rearrange our ideal gas equation. Oops, sorry. This is N equals, right? This should be PV over RT. That's a rearranged ideal gas equation. So we have 0.9747 atmospheres times the volume, 0.04175 liters, divided by the gas constant. And remember, we said we're going to use the value 0.08206. Always write the units, liters times atmospheres per mole Kelvin. I know it's cumbersome, but it helps you make sure that you have your equation properly set up. And our temperature, 297.3 Kelvin. Before you plug numbers in the calculator, make sure that the units cancel out. Let's see. I have atmospheres here and atmospheres there. I have liters there and I have liters here. I have Kelvin down here and Kelvin up here. So the moles are in the denominator of the denominator, so they're going to jump up. And now it's a matter of putting all these numbers in the calculator. And what we're going to get here is, let's go ahead and do it. Let me see what I can put this where you can see it. Oh, here we go. Okay, so let me clear all this stuff that I have here. Let's go ahead and put 0.9747 times 0.04275. Oops. Let's start again. 0.9747 times 0.04175 divided by the ideal gas equation divided by the temperature, and we get 1.668 blah blah blah. We have 4 sig figs all across here, so we're going to keep all 4 of those. So I get 1.668 times 10 to the negative 3 moles. That is our actual yield. All right. If you want to pause the video here to check your own numbers, make sure that it makes sense. Okay, let's go on now and calculate what is our actual, our percent yield. So remember that percent yield equals actual yield divided by the theoretical times 100%. Please forgive me for my bad handwriting. It's a chronic problem that I have. Okay, so let's see. Our actual yield was 1.668 times 10 to the minus 3 moles. 1.668 times 10 to the minus 3 moles. Our theoretical was 1.75 times 10 to the minus 3 moles. And that times 100% just to move the decimal place. So let's go ahead. I have it in my calculator still, so I'm going to divide by what I calculated before, 1.75 times 10 to the minus 3 times 100% equals 95.315378. But I only have 3 sig figs here, so I'm going to have to round this to 95.3%. And that is our percent yield. All right. If you want to pause your video now to check your numbers, make sure that it makes sense, and hopefully you'll get some more practice. Now, in our lab activity, we're going to do something similar to this. However, we are going to go ahead and find out. Here they gave you the actual pressure of the gas. Remember, I told you that this value here, because it's so much less than typical air pressure of 760 torr, it tells me that they really are giving you the pressure of the gas product, not the total pressure from which you had to deduct the water vapor pressure. So it's already been done for you. In our lab activity, you will have to do that step on your own. Okay? Thank you very much. All right, students, I hope that was helpful. You have many more problems to practice in your end of the chapter homework assignment. We have discussed the properties of gases. We have kind of parked on the ideal gas equation because of its multiple applications. But now what we'd like to do is let's go back into the molecular world, into the nano world, and see if we can come up with a model that will explain why do gases behave the way they do. Thank you very much.